30, the first example. 10 marbles are placed in a bag, 9 are white and 1 is red. Using a simulation method, determine the probability of selecting the red marble after 75 trials with replacement. All right, so the challenge when it comes to these kind of questions is not really coming up with the probability. It's coming up with a simulation in your calculator so that you could then come up with the probability. All right, so the process that you need to follow in order to get full credit for something like this would be defining your variables. So what I'm going to do here is account for the red and white marbles, right? So the numbers that we use in our simulation have to somehow represent these values, all right? So let's use the set from 1 to 10, all right? So 1, 2, 3, 4. Now, if there was like 100 values, you abbreviate it, like 1, 2, skip a few, 100, you know, that kind of thing. So I have 10 values, 9 are white and 1 is red. You have license to decide because they're equally sized marbles. So the probability of selecting any one marble should be the same as all the other marbles, right? So whichever one I want can be the red one and the others would be the whites, right? Generally, it ends up being the best idea to allow, if there's a singleton value, let that be the lowest number in the set, because when we sort the data, that'll be the lowest, or at least the first values that you come across. So this will be the red marble. All right, so it's assumed that the others are white, but I'll make a note anyway. All right, so white marbles. All right, so what I just need to do really is write what I would type in the calculator, and then after that, it's really just indicating what the probability is. So very easy to get full credit on a question like this as long as you know what function you're supposed to use. All right, so it's math probability option 5. So it's basically what I just did here, but let me just do it again slowly and carefully. So math probability option 5. Now you don't actually have to write math probability option 5, but what I recommend you do is give me this display, like write this out on your test paper. All right, so here my array of values are going to go from 1 to 10. And n represents the number of trials, so 75.
I did not get that on my screen.
I'll go over the other way in a minute. All right, so
Did you suppose that was enter an option 5?
yeah.
What do you get, just an open parenthesis?
Yeah, so your setup is different. I'll go over it in a second. So the lower number and the upper numbers, these are the values that you're looking to choose from. Values to choose from. Oh, why am I using this side? And the 75 is the number of trials. All right, so if you have this kind of calculator, just hit enter on paste. And then this is what comes up on your screen. Now, for those of you who have the other version, this is what came up on your screen immediately. All right, so you already had this. It's the same values. You're just typing it in slightly differently. So when you hit math probability option 5, rand int came up on your screen. You're just typing in the same values I typed in, just separated with commas. So 1, comma 10, comma 75, and then afterwards you just hit enter. All right. So depending on your calculator, you could represent it either way. The reality is, since everybody's going to get, whether you have the newer calculators or the older ones, you're all going to get to this point, because once you hit paste, it brings you to this display. If you just write this on paper, so you write how you defined your experiment, and then write what you typed in the calculator, rand int 1, comma 10, comma 75, then I know that you did what you needed to do.
Do we need to close the parentheses or just press enter?
Uh,
Option 5.
just press enter, and that'll run the simulation for you. All right. Now, the one drawback to this approach is what we kind of discovered last time, that it gives you that display, and then you'd have to scroll through the entire thing. All right. So that's kind of a pain. So what you do, and you could have done this earlier, but people.
Mine is not scrolling. It's just highlighting and I'm pressing the arrows on it.
You should. It's random. Yeah, so you should get a completely different array. If you get the same ones, that actually should be surprising. If you get the same as me, that's because you've been doing random integer function the exact same number of times as I have.
But do we need to scroll and see all the numbers?
No,
there?
because I'm going to show you how to handle it now.
Oh,
So what you're going to do is hit the store key, STO, and L1. And then hit enter. And it seems to just reproduce the values, but what it did was it stored all those numbers into list 1 in your stat editor. All right, so I'll put this in here also. All right, so again, the store key, STO with the sideways arrow. And then type in L1, second one. Yeah, that's fine. We're gonna just follow the next step and you'll see. All right. So it repeats the values. If you hit stat edit, it'll bring you into the list so that you can actually look at the list of values in the order that it's presented, but we want to actually sort this out. So I could show you, well, in a minute I'll show you, stat edit. I have some other data in there for some other stuff I was doing at some point. I don't remember what. So let me clear all that out. A little distracting. But you can see that the data values that I had originally, the 5, the 10, the 7, the 4, the 5, blah, 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 it's all in L1. So that's cool. One thing I can do is go through and count up the number of ones that are in this list. There's only 75 values. You know, I say only because I compare it to what it could be. It could be 7,500, you know, like there's always a bigger fish. It could be worse, you know, so you could scroll through and before you know it, you'll have all the relevant values, but we could also have the calculator sorted out. So you could do, whoop, undo. You can do it that way, or we can go back into our home screen. So second mode, and hit stat. Option 2 says sort A, sort ascending. Now all these steps are written on the previous page, but when you're reading it off a list of steps, it doesn't always stick. Right? So sometimes writing it yourself or just following along gets the job done. Sort A means sort ascending. That means in increasing order, which is what we want because I want to identify all the ones. If I have it organized so that the smallest numbers come first, then it's going to be really easy to count up the number of ones. So I'm going to select sort A. I'm going to hit enter, and then I'm going to type in L1 just to sort out that list of data. When I hit enter, it'll say done. Which might sound confusing because you're like, done with what? Well, think about what you asked it to do. You asked it to sort the column. So it is now done with that task. So if I go back into my list, in L1, it should all be sorted out. All right. And last time we learned that depending on the size of the data set, the sorting process could take a little while. So sometimes what people do is they start the simulation, then they work on another problem, come back, okay, that's done, sort it out, work on another problem, come back, and then that's done, and then they can finish this problem up. All right. The bottom line is, in all honesty, because look at all this stuff that happens behind the scenes. You can kind of, and I'm not encouraging this, but I do understand the realities of things, because what we're about to get in a lot of cases are a bunch of different answers for the same question, and they're all right. If it's in the right neighborhood, it's going to be correct. So you think about what you had to show me to get credit on a question like this. The answer, I mean, I'm not really as concerned with that. The probability for my simulation, the probability of getting a red, and this is experimental, because we know it should be 1 out of 10. There are 10 marbles. One of them's red. What are your chances? 1 out of 10. All right. This is telling me 1, 2, 3, 4, 5, 6 out of 75. All right. Experimentally, I got 6 out of 75. All right. So that's good. I wonder what that's equivalent to. Well, it's probably not going to be precisely 10%. But it should be in the neighborhood. So about 8%. All right. So the reality is you could totally just make up this answer and you're probably going to be okay. What I need from you is how you define the variable. So really, just anything that I have handwritten here. All the screenshots, I don't need to see any of that stuff. That happens behind the scenes. Anything that's handwritten is your work for a problem like this. All right. So this you need to know. So how to define this stuff, which is given by the setup. Then you have to give me the rand int, like what you're typing in the calculator, and then you got to give me the answer that you got from the calculator. So I'd like for you not to fake this process on the test, but I also know the reality of things. Right? So, because I've had people like fess up afterwards. You're like, I got away with one there. I just wrote the steps, and then I took what I knew the probability was going to be, 0.1, multiplied it by 75, that got me 7.5, and then I just chose a number that was close to that. So 7.5, so they would say I got 7. I did all this work, I swear. I got 7 out of 75. I got 8 out of 75. I got 9 out of 7, something in that neighborhood. And I'm like, okay. That stinks. I wish you didn't do that, but I'll take it. No. So, because the question related to this on the test is supposed to be one that everybody can get full credit on. It's supposed to be a gift. but it's also it's supposed to be something that you could find value in too, right? Because when you are collecting data, there will be an element of randomization that you're going to want to include in that when thinking in terms of the paper in the third unit. This technique is something that'll be really helpful for you, right? So the second example, in the 2015 baseball season, the population mean percentage of instances in which a team scores could depend on whether the leadoff hitter reaches base. Use the information below to simulate the number of innings in a game in which a team would score at least one run. And the notation is there are typically 9 innings in a game. All right, so it's kind of weird because it sort of seems to imply that you need to know a little bit about baseball, but I created a tree diagram to really illustrate what's going on here. So it's conditional. We have a yes or no, and then based off of that yes or no, we have another yes or no. So we just got to think about what the yes or no's mean. All right, team gets leadoff batter on base in a given inning. All right, whatever that means. All right, so leadoff hitter reaches base. And that's a yes or no. I don't know the breakdown of that. So what we can do in the absence of information, we assume all things are equal. So we'll say that that's 50-50. All right, so 0.5, 0.5. So the Y in the ends represents whether or not a run, at least one run scores in the inning. All right, so what's happening here, and really we're just designing the experiment, because actually conducting the experiment is sort of a pain. So let me say, to design the simulation, all right, because we won't actually carry it out because it's too much of a pain, right? Because to go 9 innings and then try to keep track of how many scores there would be, that would be too much, all right? So both of these yeses represent at least one run scores. And this is real data. So if you're even remotely interested in baseball, this actually came from a Mets broadcast in 2015. The general manager at the time was talking about it, and he was saying that this is a fact. They ran the analytics, and this is a fact. When the leadoff hitter gets on base, the team in which that leadoff hitter gets on base scores at least one run. Now they could score 10 runs, but they're good for at least a run in that inning about 57% of the time. All right. Now, I did a little further investigation, and it turned out that when the leadoff hitter did not reach base, that the team would typically only score 16% of the time. All right. So, that's a stark difference between the two possibilities. All right. So, but again, it's scoring at least one run. So that's 16% of the time. Again, it could be one run, or it could be 15 runs. You could, that 16% of the time could lead to the inning in which you win the game, right? Like the 4th inning yesterday, right? If you watched, I'm only watching now the World Series now because I don't like some of the players on the Astros. It's about people now. It doesn't really have anything to do with teams anymore, because as a Mets fan, I should be rooting against the Nationals, who are technically a rival, but they're like, I don't really care about them. Also, Bryce Harper is kind of I can't say the bad word that I want to say. He used to play for the Nationals, and they couldn't win when he was there. Like they couldn't win a playoff series, and so he left the Nationals and went to the Phillies, and now the Phillies suck, and the Nationals are in the World Series, and so that would really make me happy if this guy who's like not a good person could experience the pain of realizing that he was the reason why they couldn't win. That like spoiled professional athletes, I really like it when they get their comeuppance. So that's hopefully will be happening within the next few days. Anyway, so the simulation here, I just have to come up with a 50-50 for the leadoff hitter. So it's multi-level. If you were to carry this out, it wouldn't be difficult, but just writing the setup is all I would really need. So for the leadoff hitter, I'm going to let 0 equal not reach base. And 1 represent reach base. All right. So that should be easy enough because inning by inning, what we'll do is a random integer between 0 and 1. Now, you could choose any 2 consecutive values. I just chose 0 and 1. Right. It's a typical way of representing failure and success. 0 being 0% chance of succeeding and 1 being 100%. So it kind of feels right. And so in the set of 1 to 100, right? So 1, 2, 3, all the way up to 100. 98, 99, 100. We could also define some variables. Or some values, I mean. Keep saying variables. And it'll be conditional, all right? So we have 2 cases. Leadoff hitter on, the leadoff hitter reaches. Then the set of values, jeez. We just need 57 values from the set of 1 to 100 to represent scoring a run. So 1 through 57, and I'll leave the squiggly brackets out because I seem to be struggling now making them. 1 to 57. You score at least a run. The rest, so 58 to 100. If you didn't score at least 1 run, you didn't get anything, so no run. And again, if you have absolutely no familiarity with baseball, I'll just say that a run is a point, all right? So if you like soccer or any other kind of sport, you know, like there's a way in which you could achieve a success. A run is how you achieve success in baseball, all right? So that's how we keep score. So the other possibility is that the leadoff hitter did not reach base. So I'd make a note of that. I'll do that in a different color.
So N stands for not there. The N stands for not.
The N?
See where you have the Y and N?
Yes, exactly. Sorry about that. Yeah. Leadoff hitter not reach. So the other case, because again, it's conditional. So we use the random integer to determine which category we fall in, and then we use a second random integer to determine what happened once we're in that category. Okay? So if that's the case, then 1 through 16 would be score at least one run. And then the rest, 84 to 100, 84 to 100, geez. We need another 84 values, so 17 to 100 would be no run. All right, so obviously we stepped up the level of difficulty here because it's multi-level. We have two different integers that we have to account for, and also we branched out. We're not dealing with cards, dice, marbles in the bag, things like that. It's a real life situation. And just like I was talking about before with barometric pressures, it could be a real life situation that you have no interest in. Right? So you look at it and say, okay, I'm going to draw a conclusion out of this that I absolutely I don't give one iota about. Right? But if you take this concept and apply it to something that you do have interest in, then it could be more meaningful for you. All right? So to run the simulation, the first thing I'd have to do is a random integer, and we don't need to use lists or anything like this. Random integer on 0 to 1. Then a random integer on 1 to 100. All right. And that would determine if a team is going to score at least one run in an inning. And then we could verify that these probabilities are or are not correct. All right. So we could run the simulation, but like I said before, doing this for 9 innings, that's a little much. I'll just do it for 1 inning so you see. All right. So math, probability, option 5. I'm just doing one trial at a time. So 0, 1. That's why I didn't put the number of trials after that. It's just a 1, or if you leave it blank, leave n blank, it's just going to choose a single value from that interval. So 1 trial got me 0, which means my leadoff hitter did not reach base. All right. So then what I would do is math, probability. This time going from 1 to 100. And then see what happened. All right, so you could already see how much of a pain this would be just by typing stuff into your calculator, because I'd have to go back and forth between the two random integer functions, so very, very aggravating. But following my tree diagram or my elaboration here, I would say, okay, I didn't reach base, and I'm in the 44. Well, I'm in the 17 to 100 category because I got a 44, which means the individual did not reach base and the team did not score a run. All right. So first you categorize it based off reaching base or not, and then this pigeonholes you either into the blue or the red. Because I did not reach base, I'm in the red. So then the second number is either going to fall into the first or second category. So it fell into the second category, so no run was scored, which is kind of what we expected. All right. So let's say, for example, that first integer, which is really amounting to the flip of a coin, let's say that ended up being a 1. That would have put us on reaching base, and let's say that the second value still ended up being 44. We would have scored at least 1 run. All right. So you can see, even with the same number, just by being in a different category, it leads to a completely different outcome. All right. Now, is that going to tell me every little detail that happened in an inning of baseball? Not, probably not. And again, it completely neglects. I can't simulate a final score of a baseball game here because at least one run, like I said, it could be 20 runs or it could be one run, right? So, or anything in between. So, like if I simulate 9 innings and it turned out that a team scored at least one run in each inning, that means they could have scored 9 runs at a minimum, or they could have scored infinity runs at a maximum, right? Because maybe they scored like 100,000 runs in one inning. You know, I mean, it's never happened, but I guess it's possible. All right, they don't have a mercy rule in professional baseball.
Can you go back a second? So you go, you didn't get the 0, you got the 1.
If I got the 1, that would put me in the blue category. So then that 44 would fall in this first interval, which would put me in the score at least 1 run. It's a different outcome based off of the condition. All right, but you could see, like, definitely at a minimum more elaborate.